This is part 3 of our series of probability lectures. This one is on empirical probabilities and the law of large numbers. This is Jack Jackson. Before we proceed with this presentation, you need to be sure that you get a fair coin to flip. And you may also want to go ahead and get your calculator or some other device on your computer or your phone that will allow you to simulate flipping a coin a lot of times. So we're going to be doing some experiments during the middle of this presentation where we're going to be flipping a coin. So be sure that you get these together. So if you don't have those together yet, just stop this right now, go back, get your materials, come back and start over. Okay, now everybody should have a coin. So let's go on. First thing we're going to do is define what we mean by the word empirical probability. In a finite sample space, remember that probability is similar to relative frequency. If you remember what we did, we just took the size of the event divided by what we're going to do now is define empirical probability. What you'll notice is that in a finite sample space, probability is similar to relative frequency. So remember that in a finite sample space, when you did a probability of an event, that it was the size of the event divided by the size of the sample space, assuming all the simple events were equally likely. And that gives us a basic probability, and that's just a relative frequency if there's actually a data set that has a data point for every element of the sample space. And again, they're equally likely. So because of this similarity, we can use experimentation to approximate actual probabilities. So actual probabilities are done not from experimentation, but by understanding the parameters and how the structure of the experiment works out. Okay. For example, we flip a coin. We know there are two outcomes, heads and tails. We know they're equally likely, so we know the probability is 50% heads and 50% tails. That's from understanding the structure of it. But we can also do an experiment. So we repeat our probability experiment a whole bunch of times. Then we can use the relative frequency of an event to estimate the probability of the event. This estimate is actually a relative frequency. It's not really a probability at all, but we often call it an empirical probability or experimental probability. And it's often a good estimation of the actual theoretical probability, and so that's why we call it a probability even though it really isn't one. So what we can do is, using these experiments, we can estimate the probabilities using these empirical probabilities. That is called a simulation. So we can use simulations to do that. Occasionally you'll hear this referred to as Monte Carlo methods. That's after the place in Europe where they have a lot of gambling, Monte Carlo. So let's take an experiment here. We're going to do a basic coin experiment. We're just going to flip a fair coin. So first of all, let's just review what is the sample space and what's the probability of each event in the sample space. Okay, well, we know that the sample space is either just the set containing heads or tails. We'll just abbreviate that H and T. And the probability of the heads equals the probability of the tails, which is 1/2 or 0.5 or 50%. Does this mean that if we flip a coin once, then it will come up 50% heads and 50% tails? Well, of course not. It'll either come up 100% heads or 100% tails. There's no way it can come up half heads and half tails when you just flip it once. Well, what if we flip it twice? Well, let's actually try it. We're going to have you do this in just a second and actually flip your coin and write down your results. Do you expect to have 1 heads and 1 tails? Would you be surprised if you got 2 heads or 2 tails instead? So actually do this once. What did you get? I'll do it right now. I got a heads and I got a heads. Okay, was that surprising? Okay, now do this experiment 10 times, so we'll get 10 pairs of either heads or tails or some combination, and record that. What do you notice? So get your coin out and let's do this experiment, getting 10 pairs of data. We're going to press pause, let you do your experiment, and then come back after you've done it and record it. Please press pause now. Okay, now you should have your 10 pairs of data. What did you notice? Well, one thing you're probably going to notice is, as with any probability experiment, we don't know the results ahead of time. They're going to vary from time to time. That's sort of the whole idea is that we're dealing with in this course is things that are completely, not completely uncertain, but they are uncertain. We don't know what's going to happen for sure. Now we'd expect with about half heads and half tails, so with 10 trials we should expect around half of them, we should expect a heads and a tails each one, but there's going to be lots of times that you're going to get not always half tails and half heads, one each, but you're going to get, some of them are going to be all tails and some will be 100% heads. So we don't expect the relative frequency to be exactly equal to the theoretical probability. Now, we're going to repeat this experiment, but this time instead of only flipping twice, we're going to flip the coin 100 times and record the results of each flip. And then we're going to total up how many heads and how many tails you get out of that 100 times. What do you expect to see? Should we expect to see maybe close to how many? 50 heads? 50 tails? Would we be surprised if it's close to that? Would we be surprised if it's right on? Would we be surprised if it's way off of that? Actually do it and try it. And then after you finish that, then we want to do this 1,000 times. Now, if you want to do this 1,000 times, you might not want to actually sit there and flip the coin 1,000 times. So here's where you might want to get a simulator out, like the coin flipping simulator on your calculator. There'll be another video that shows you a little bit about how to use the simulation, probability simulation software on the calculator. Or you might have an app for your smartphone, or you might have some kind of software for your computer or a website or something that will simulate flipping a coin. There's lots of them available. So either physically flip a coin 1,000 times or just use a simulator. It's actually kind of cool to actually physically flip the coin a few times, so I suggest you actually physically flip it the 100 times, but you can of course use a simulation for that. Now again, what do you expect to see? Okay, let's actually do this now. Please pause now. Okay, now we're back. You spent a little bit of time doing some simulations, hopefully, and you got some results. Well, what would you expect? You'd expect there to be about 50% heads and 50% tails. So for 100 flips, we'd expect close to, but probably not exactly, 50 heads and 50 tails. Would we be surprised to get 45 heads and 55 tails? Probably not too surprised for that one. It's possible. What about 10 heads and 90 tails? What about all heads in 100 flips? Oh, that's a pretty rare event there. We would be very surprised to get 10 heads and 90 tails, and extremely surprised if they all came up heads. I start to suspect your coin only had heads on both sides or something like that. So that it might not really be a fair coin, because it'd be much more likely in that case that it's not a fair coin than it is to have actually just randomly gotten those results. Okay, so let's continue with this idea a little bit. Suppose we flip the coin 10 times. We could get 7 heads and 3 tails, 70% heads. We flipped it 100 times, it's possible we could get 70 heads and 30 tails. Again, 70% heads. If we did 1,000 times, we could get 700 heads and 300 tails. 70% heads. What do you think? Which would be the least surprising of those three results? Flipping it 10 times and getting 70%, 100 times and getting 70%, or 1,000 times and getting 70%? Which would be the most surprising? Well, wouldn't be surprising at all to flip 10 times and get 7 heads. That's not necessarily that surprising. 100 times and 70 heads, that's pretty unusual. We would be pretty surprised to see that. But if we flipped it 1,000 times and got 700 heads, 70% heads, we would be very surprised with that. That's a very unusual event. In fact, we would start to suspect that something is not really random about the way we're flipping this coin. So this leads us to a very important concept, and that is the law of large numbers. As the number of trials of a probability experiment increases, it is less and less likely that the experimental relative frequencies will differ significantly from the theoretical probabilities. So if we repeat the experiment a large number of times, then we expect the relative frequencies, also known as empirical probabilities, to approximate the theoretical probabilities very well. This phenomenon is known as the law of large numbers. So basically the idea is if we repeat the experiment a lot of times, hundreds, thousands of times, maybe even more, then we would expect our relative frequencies to line up pretty well with the theoretical probabilities. This law of large numbers can be counted on. And in fact, we can actually compute some probabilities here. So using techniques that we'll discuss later, we can compute the probability, rounded off, that a particular number of flips of a coin will result in fewer than 45% or more than 55% heads. We expect around 50% heads because that's the actual theoretical probability. We don't expect to be far off. You know, somewhere between 45% and 55%, we'd expect most of the time we would be in there. If you flip 4 times, it turns out you've got a 62.5% chance of being either less than 45% or greater than 55%. But if you increase that to 10 times, that's 75.4%. Okay, but if we start increasing it more and more, we start to see this percentage drop. If you go to 100 times, that percentage drops to 27.1%. Wow. So just going from 10 to 100 times, we're dropping that percentage that it could be very far away a lot. If you go to 500 times, that drops again all the way to 2.2%. And if you do it 1,000 times, like we did in the experiment earlier in our simulation, there's only a 0.14% chance that the number of heads, the percentage of heads, will be less than 45% or more than 55%. So we'll be within 5% of the true theoretical probability over 99% of the time if we did this with 1,000 trials. So you can see those numbers after you get started here a little bit with the really small numbers. Then as the numbers get bigger and bigger, these probabilities drop dramatically. And so we see that this law of large numbers, there it is in action. Now this is so much a fact that we can count on that there's a whole industry that banks on this, the casino industry. Casinos bank on the law of large numbers to give them their income. So let's just take a simple example, maybe a simplified example of a simple game that you might see in a casino, and that's a roulette wheel. In America, the American version of the roulette wheel has 36 slots, numbered 1 through 36. Half of them are black and half are red. So that's 18 black and 18 red. But then it also has another 2 slots that are green. You can see them there in the wheel, there, a picture of it. A green 0 and 00 slot. So basically what happens is they give this wheel we give a ball a spin around the wheel, and we spin it. The ball's rolling and rolling and rolling around. Eventually it stops and it falls down into the wheel into one of the actually 38 slots. Now there's actually other bets that you can do with a roulette wheel, but let's just assume that this particular roulette wheel, we have the most simple bet. You either bet on black or you bet on red. In other words, you bet that ball will land in a black slot or you can bet that it'll land in a red slot. The payoff odds are 1 to 1. Now, when you see payoff odds, they're not true odds. Okay, so we're going to compute the true odds in a minute. The payoff odds are 1 to 1. So what we mean from this is if you bet some money, so say you bet on black, okay, and if black actually, the ball lands in the black slot, so black wins, you get your money back, plus you get $1 of winnings for every $1 that you bet. So if you bet $4 and black wins and you bet it on black, then you're going to get your $4 back that you bet plus another $4. So you win $4. Now, what I'd like you to do is go ahead and do some computations here for me. What are the actual odds against black? And hint, they're not the payoff odds, so that's why the odds is in quotations there. They're not really odds when they do a payoff. What are the actual odds against black? And then go ahead and figure out the probabilities of a black, a red, and a green. So go ahead and figure those out, and then we'll come back. Please press pause now. So, what are the actual odds against black? Well, there are 20 that are not black and 18 that are, so that's 20 to 18. We can reduce that to 10 to 9, and of course we can also divide both those by 9 and get a decimal, 1.1 repeated to 1. So it's bigger than 1 to 1. Okay, longer odds are less likely than the payoff odds. So the probability of black and the probability of red are both the same. It's 18 over 38 reduces to 9 over 19, or about 47%. Probability of green is 2 over 38, or 1/19. That rounds off to approximately 5.26%. So let's see how this works here. 95% roughly of the time, what happens? You have about the same amount bet on black as you do on red. And so what happens is red wins. You take the casino gets to keep the money from black, but they got to pay off red. So basically what happens, they're just taking the money from the people who bet on black and giving it to the people who bet on red. And when the other one wins, the money flows in the other direction. But that's not hurting the casino any. It's not really helping them either. They're just getting that money changing hands. But look what happens 5.26% of the time. 5.26% of the time, that ball is going to land in a green slot, and what happens? The casino takes everyone's money, and that is what they're banking on. What does the casino want? They want a volume of business, big, large volume, so that they can get that 5.26% of a very large number. That's the law of large numbers in action. That is what the casinos bank on. They know that on average they're going to get a little over 5% of every dollar bet. That's what they're gonna make as profit on that particular game. And again, this is a little bit simplified version where we only have those two bets, but that's the basic concept of how casinos work. If you want to go to the casino and have a good time, I don't have a problem with that, but realize that it is stacked against you. That if you do it a lot, you can probably bank on losing about 5% of your money on this particular game. So, in conclusion, we can use experimentation to simulate a probability experiment, and we can be fairly sure that the empirical probabilities, that is, the experimental relative frequencies, will be fairly close to, but probably not exactly right on, the actual theoretical probabilities if the number of trials is very large. The larger the number of trials used in the simulation, the more confident we are that the empirical probability is a good estimate of the theoretical probability. So that gives us a nice little introduction to using simulations to compute empirical probabilities to estimate actual theoretical probabilities, and it's based on this law of large numbers.